Hi everyone, so in this video we're going to talk about the unit circle and how it relates to trigonometric ratios and allows us to define trigonometric functions. So up until now, when we're thinking about trigonometric ratios, you'll probably have thought about some right-angled triangle with some angle theta, and based on the angle that we're looking at, we can label the sides opposite and adjacent to that angle and the hypotenuse. And the two trigonometric ratios that we're going to be most interested in this video are going to be sine of theta and cos of theta. Cos of theta we know is the adjacent over the hypotenuse, and sine of theta is equal to the opposite over the hypotenuse. So that you'll already be familiar with. However, this definition is limited to the right-angled triangle that we can draw, and therefore it only allows us to consider when theta is acute, so it's between 0 and 90 degrees. The unit circle we're going to take a look at allows us to expand that definition of trigonometric ratios of sine and cosine. So if I draw myself a unit circle, what do I mean by that? If I draw myself a nice set of x, y axes, I'm going to draw a circle on those axes. And if it's a unit circle, all it means is that the radius is 1 unit. So I can draw in some radius, say here, and the radius r is equal to 1. Okay, and that's the case all the way around. So here we cross out 1, here we cross out -1, -1, and 1. So that's my unit circle. Okay, why is this relevant? If I look at this line that I've drawn, that orange radius that I've drawn in, and I want to think about the x, y coordinates of this point here on the circle, the point where it hits, the radius touches the edge of the circle. Okay, I can define the angle here as theta. And if I think about the x and y coordinates, well, the x coordinates sort of draw in. My x coordinate will be somewhere there, and my y coordinate, you can imagine, will be somewhere there. And I want to think about how I can define those in terms of the angle. You'll notice that here, drawing this vertical line and this horizontal line along the x-axis, I have a right-angled triangle. And that allows me to use the trigonometric ratios that I saw previously of sine and cos to describe some of the lengths in this triangle. So cos of theta, we said previously, was the adjacent side opposite the hypotenuse. Now, my hypotenuse on this triangle here is the radius, and that's just 1. The adjacent, here's my angle theta, the adjacent side is whatever's going along the x coordinate, right? This is my adjacent side, it's going along the x-axis. So I can say that cos theta is equal to the adjacent, so the x coordinate over 1, which is just x. I can do the same thing for sine theta. We said that was opposite over the hypotenuse, and my hypotenuse is the same, it's just 1. If theta is my angle here, the opposite side is this side, and that represents the y coordinate, so the distance in y. So it's just going to be y over 1, which is just equal to y. Okay, why is that particularly useful? I can draw any other line. I could draw another line here, another radius also of length 1, and I could do the same thing. I could draw a little right-angled triangle, and it would still be the case that my xy coordinates will be cos theta, sine theta. Exactly the same as here, where cos theta, sine theta are my x and y coordinates. Obviously, the angle theta has changed, but it allows me to describe the x and y coordinates of the point on the unit circle in relation to the angle. Let's think about what happens when we use the unit circle for what it's designed for, which is extending this angle of theta so that it's greater than 90 degrees. So we're going to pull it all the way round into the second quadrant. All I'm going to do is I'm going to draw the same radius here as if it's perfectly reflected in the y-axis. So we draw something like this, some coordinates here, and I'm going to make it so that this angle is also theta 1. Now this is not the convention for measuring angles on the unit circle. We always measure from the positive x-axis anti-clockwise, but it's just to make you aware that I've drawn it symmetrically so that the size of this angle is the same as the size of this angle. However, if we want to define the angle at which this radius is, we need to do it in the way I mentioned. We need to start at the positive x-axis and we need to go round anti-clockwise. So this is going to be my angle theta 2. We can see, based on that diagram, that theta 2 plus theta 1 make a straight line. So we can say that the angle theta 2 is equal to 180 degrees minus theta 1, or if we're working in radians, pi minus theta 1. That's going to become useful in a moment. You can see I can draw the exact same sort of mini right-angled triangle based on where this radius, the pink radius, hits the edge of the circle, again to determine the x and y coordinates of that point on the edge of the circle. Now, because we'll think about the x coordinates first. So we've said, although my drawing is not perfect, it's a perfect reflection in the y-axis. So this angle is the same as this angle. So therefore, this distance in x, i.e. the x coordinate, we said was cos of theta 1. And that means that this x distance here must be the same. It's the same distance. However, we're now in the negative part of the x coordinates. Let's add in, just to be super clear, we're talking about x and y here. Okay, so this x coordinate here is minus cos of theta 1. And we said that any point on the edge of the circle, here for example, the xy coordinates are defined by the cos of the angle that takes you from the positive x-axis anti-clockwise to this arm. So in this case, theta 2. So this x coordinate is the cosine of theta 2, okay, and the y coordinate will also be the sine of theta 2. Well, I can look at the x coordinate of this pink point, and I can therefore say the x coordinate is equal to the cosine of theta 2. But we can also see that that's the negative cosine of theta 1, just by the symmetry of these triangles. When I look at the y coordinate, we can see that they're identical. So my y coordinate here, sine theta 2, is going to be equal to sine of theta 1. Let's just make it super clear. Over here, theta 1, theta 1. Okay, so my y coordinate, I can see that the sine of theta 2 is equal to the sine of theta 1. I can use this fact that I stated earlier to determine a relationship between different angles and their cosines. So instead of having cos of theta 2, I can write theta 2 in terms of theta 1. This is cos of pi minus theta 1. And this is sine of pi minus theta 1. So these are some useful relationships that you don't need to learn by heart, but just understand how we get them from this unit circle. But this is great. This has allowed me to define a sine and cosine of an angle that is greater than 90 degrees, or greater than pi over 2. If I draw another radial arm in, let's say in this case I draw something all the way down here, this is going to be defined. I have to start at the positive x-axis and go all the way round. That will be my angle theta 3. And again, my xy coordinates will be defined by cos of theta 3, sine of theta 3. So this is now defining the sine and cosine of a reflex angle. So that's defined sine and cosine for some quite large angles as we go all the way around the circle. But there's nothing to stop us going around the circle more than once or going around the circle in the opposite direction. What do I mean by that? So let's draw ourselves another unit circle, x and y coordinates. X coordinate will always represent cos theta, y coordinate will always represent sine theta. Okay, and if I start defining my angle theta, and I always start on the positive x-axis, and I go anti-clockwise. So I go round. I've done 360 degrees, or 2 pi, and let's say I go a little bit further. I can draw in the radius that will be represented by that. Well, again, here's my angle theta. My x-coordinate is cos theta, my y-coordinate is sine theta. And this is for theta is greater than 2 pi, or 360 degrees. I can go round the circle millions of times. So all of a sudden, I can go as large as I like with my angle theta, and I can define the sine and cosine for it. I could do the exact same thing. Let's draw out another unit circle, and let's go the other way round it. So here's my circle. Let's draw some radius in here. Now, by the previous convention, to figure out the angle theta, we would go from the positive x-axis anti-clockwise. However, I could also get to this radius by going in that direction. And if this is my angle theta that I choose to include, going clockwise from the positive x-axis, well, we said by convention anti-clockwise is positive, therefore in this case theta will be negative because I've gone clockwise. So I can therefore define this sine and cosine, so cos of theta will be the x-coordinate, sine of theta will be the y-coordinate, for theta being negative, being less than 0. And again, I could go round multiple times in the negative direction. There's no end to how negative theta can be. So all of a sudden, by using the unit circle, I've been able to define cosine and sine of angles that are hugely negative or hugely positive without any limit on them. So now that we've seen that we can do that with the unit circle, I want us to draw a function for cosine theta and then for sine theta, describing how they change as theta changes. We're going to think about this using the unit circle. So we'll think about cos theta first. So here's my unit circle, and I'm going to draw out a separate set of axes that's going to represent the function that I want to draw, where I'm measuring theta on my x-axis, and I want to know how cos theta changes on my y-axis. Okay, so different axes to the ones I've used for my unit circle. Well, we're going to plot some points to plot the function. So let's start with theta being 0. Okay, theta being 0 is here on my graph axes. Theta being 0 on my unit circle is here. I've started from the positive x-axis and I haven't moved around at all. And so I want to know when theta is equal to 0, here, what is cos of theta? Well, we said, as always, cos of theta is equal to the x-coordinate on the unit circle. Now, the x-coordinate on the unit circle here is 1. We'll mark in some key points. By definition, remember, the unit circle has a radius of 1. So straight away on my graph to the right, I can say that when theta is 0, cos theta is 1. And then I want to sort of draw this graph moving along to the right, so increasing theta. So I'm going to consider sort of moving this radius round the circle in that direction, anti-clockwise, increasing theta. I want to think about what's happening to cos theta, or we can just think of that as the x coordinate. So when I first increase theta a little bit, my x coordinate, my circle's not drawn perfectly, but my x coordinate has decreased slightly. As I continue to sort of move around the edge of the circle, so as theta increases, my x coordinate continues to decrease, and you can see that at the start here, I'm mainly moving upwards along the circle. I'm not interested in the y coordinate, so I'm not interested in the moving upwards, but I'm not moving to the left very much. As I start to move further round this quadrant of the circle, the rate at which I move left, so the rate at which the x coordinate decreases, increases a lot. So we can say at the start we're decreasing, so cos theta, which here is on my y-axis, is sort of decreasing, and the rate at which it's decreasing is increasing. It gets steeper and steeper. When we get to an angle of 90 degrees, or pi over 2, we can see that the x coordinate, so cos theta, is equal to 0. So here, my angle that I've moved through to get there is pi over 2, or 90 degrees. And my x coordinate, so cos of pi over 2, or cos of 90 degrees, is equal to 0. Okay, what happens as I continue to move round this circle? So we'll think about the next sort of quadrant. As we continue to move round, theta continues to increase. Okay, so again, we're thinking about what's happening to cos theta as theta increases in this part of the circle. So I'm just saying, as I move anti-clockwise, what's happening to the x coordinate? Well, in this part of the circle, we can see the x coordinate is negative. In the whole of this part, all along here, we've got a negative cos theta because we've got a negative x coordinate. And initially, we decrease or become very negative in the x coordinate quite quickly. Most of the movement is horizontal along this part of the circle. But then the rate at which it becomes more negative decreases. We have more vertical movement along the circle, which we don't care about, and the x coordinate doesn't change very much. For example, between here and here, we see the x coordinates, as opposed to between here and here. Okay, so we get a negative x coordinate, a negative cos theta, that is initially decreasing very fast, and then the rate at which it decreases. When we get to here, so here we're at an angle, let's label in those angles, it might be easier to visualize. So here we said we have an angle of pi over 2, here we have an angle of pi, or 180 degrees, 90 degrees. So when we're here on the circle, and we've got an angle of pi, my cos theta, or my x coordinate, is -1. So on my graph over here, I know that this point here occurs when I'm at pi, or 180 degrees, and I have a minimum of -1. Okay, let's move around the next section of the circle. Again, I'm staying negative, my x coordinate is staying negative, but it's becoming less and less negative. So I'm sort of moving this way along the x-axis as I move around the circle like this. Initially, most of my movement is vertical, it doesn't really become less negative very quickly, and then as I move around, here there's a big change in the x coordinate, and as it approaches 0. So by the time I get round to here, so I'm now at an angle of 3 pi over 2, or 270 degrees. I've moved around, my x coordinate is 0, so I can get that in ready on my graph. So this is an angle of 3 pi over 2, or 270 degrees. and we get the same behavior. So initially, it doesn't really become less negative very quickly, and then it becomes much less negative as we move to the right along this part of the circle. Then I need to think about the last quadrant, which will be up to 2 pi or 360 degrees. So that's as I'm moving through this part. And again, as I'm moving through this part of the circle, my x-coordinate is now positive. It increases a lot. I have a lot of horizontal movement in this chunk of the circle as opposed to this chunk of the circle. So I get a lot of positive movement, and then it tapers off until I reach 2 pi, and my x-coordinate, or my cos theta, is again 1. So I've drawn the behavior. This function on the right is telling me how the x-coordinate on the unit circle, or cos of theta, is changing as I go round the unit circle, i.e. as theta is increasing. Now, we said previously we can go around the unit circle many times, so theta doesn't have to stop at 2 pi. So I can draw myself another graph, just extending the domain of cos theta. And this time we'll say we'll get up to 2 pi about here. We'll have pi, 3 pi, 4 pi, etc. And we also said we can go the other way around the circle. And let's have minus pi, minus 2 pi. So thinking about what's going to happen, well, we've seen this is my general behavior for the first revolution. Okay, I've squished the scale a little bit so I can fit it in. When I go around the circle again, I'll just get the exact same behavior. So this will just continue for however many times I go around the circle, however many periods round the unit circle. If I go the other way, again, okay, my theta is defined as negative, but I still get the exact same behavior. So I'll get a graph that looks something like this. And again, I can extend that in any direction. Okay, my drawing is not great. I should have a maximum everywhere of 1 and a minimum everywhere of -1. So this oscillating function is defined by the unit circle as we go round and round in either direction, and it allows us to plot the function of cos theta against theta. You probably guessed what's coming next. We can do the exact same thing, this time for sine theta. So if I draw in my unit circle, got my x and my y coordinates, my unit circle, as always, has radius of 1. So we can pop in some coordinates here. And this time we're thinking about sine. So we defined previously that sine theta is equal to the y coordinate on the unit circle. So the thought process is exactly the same, except instead of watching what's happening to the x coordinate, I'm watching what's happening to the y coordinate. So this is sine theta, this is theta. Okay, so let's start at theta is 0, so somewhere around here, so we can start drawing our graph. Okay, when theta, if I draw in the radius when theta is 0, I just get to this point here, the point 1, 0 on the unit circle. Well, my y coordinate is my sine theta, and we can see that's also 0. So I'll start at 0, 0 on the graph on the right. As I then move round the circle, so as I'm increasing theta, we've got various coordinates, and we're interested in the y coordinates. So the same thought process. When I start from theta is 0 and I increase it, initially we have a very fast increase in the y coordinate. Most of my motion from here to here is in y. So the y coordinate increases. From here to here, okay, it's still increasing, but there's more sort of x movement and y isn't increasing as much. And then from here to here, this chunk, okay, I increase in y, but very little. So initially we have a very steep increase in the y coordinate, and then it kind of flattens off. So we get this first part of the graph, and that takes us to here. And we said this is at an angle of pi over 2 or 90 degrees. Then we're going to think about what happens in the next quadrant, just like before. So if I draw in, if you imagine theta now continuing to increase around here. Okay, so I'm at a maximum y value of 1. I can put that in on my graph actually, here's my maximum point. As I increase theta slightly more to this next point, my y coordinate has decreased very slightly. And then as I continue to move around, my y coordinate decreases faster and faster until I get to here. So I get sort of a slow decrease and then a very quick decrease until I get round to here, an angle of pi or 180 degrees. And then again, we can see my y coordinate, or my sine theta, is 0. This is at pi. Again, same thought process. What's happening as we're continuing to move around the circle? Well, my y coordinate is now negative, so sine theta is negative in this quadrant. And initially, it gets negative very quickly, and then it's still getting more negative, but at a slower rate, up until 270 degrees, or 3 pi over 2. So we get this next sort of chunk of the graph. And at 3 pi over 2, down here, we have a y coordinate minimum, so a sine theta minimum of -1. So -1 is my minimum down here at 3 pi over 2. And again, I go through the same thought process as I continue to move around the circle, so theta continues to increase. So the whole time I'm going round, although my sine theta, my y coordinate, is going from positive to negative, because I'm always moving anti-clockwise, theta is always increasing. So on my graph, I'm always going along, if this is describing what's happening to theta. And initially, my y coordinate is becoming slightly less negative, and then very, very, very much quicker, much more quickly less negative. So my final quadrant of the graph looks like this. And when I get to 2 pi, to a full rotation here, my y coordinate sine theta is 0. So just like with the graph of cos theta, we now have a full cycle. You'll notice that basically the exact same behavior is displayed in the sine theta and cos theta graph. They're just out of sync with one another. Cos theta starts at 0, 1, whereas sine theta starts at 0, 0. And just like using the same concept as we did for cos theta, I can draw my graph of sine theta against theta. And again, I can go round the circle as many times as I want. So this would be my first full cycle up to 2 pi. When I get over here to 4 pi, I've done 2 loops of the circle, and I can go around the other way as well. And so my graph can extend in either direction as far as I want, with a constant maximum of 1 and a constant minimum, of -1. So those are my trigonometric functions. You'll often see as a note, instead of it written as sine theta, you may see it written as y equals sine x. And you'll just have x on the x-axis here, where this will be the angle on your unit circle. Likewise, you might see y equals cos x. Again, this is your angle. I've kept it as theta separately for this example to distinguish between the x and y coordinates on the unit circle as opposed to the x and y coordinates on the graph. They're not the same thing, but you'll see it like this in future. These graphs of the functions of sine theta and cos theta become particularly useful with solving equations. So if, for example, you imagine, scroll down slightly, you had the equation sine theta was equal to 1/2 that you needed to solve. Okay, traditionally you would have done theta is equal to the inverse sine of 1/2, and you would get one solution out. However, when I've got the graph drawn in front of me, as you've used your graphical calculator form many times before when solving equations, if you have an equation that you need to solve with a variable on the left and another equation or a constant on the right, you simply graph both those things. So we've got the graph of sine theta plotted, and if I just draw in a line at 1/2 here, we can see that, okay, we have a solution here, but we also have a solution here. We also have a solution here, a solution here, a solution here, a solution here that you could just find using the intersection on your calculator. We have infinitely many solutions. Perhaps you're asked to solve this for theta is between 0 and 2 pi, in which case you'll have this solution here, this solution here, this solution here. Apologies, not those two solutions because they are greater than 2 pi. So it would just be these two solutions that were appropriate for that specific equation with that stated value for theta. But it allows us to solve trigonometric equations, just graphing the functions, which we'll do kind of without thinking, to solve for multiple solutions. Although you might do it without thinking, and when you've done a few practice questions of this, you'll just plot the graph straight away and find the intersections. It's important to understand where these graphs come from, their origins from the unit circle.